All right, clip number 3 for chapter 11, section 7 notes on surface area and volume of a sphere. This clip is going to focus on the latter part of the title, the volume. And that formula you see at the top there, it's intimidating to students for a couple of reasons. I'll talk about those in a second, but that's literally the formula we're just going to be using for the volume of a sphere. And what we're seeing there actually tracks with the fact that we're finding a volume, the amount of space on the inside of a three-dimensional object. A three-dimensional measurement would have cubic or 3 to the third power units for that whatever unit of measurement there is. That tracks here with the right-hand side of the equation. Radius, again, of a sphere is a one-dimensional measurement. It's simply a distance from the center to its edge. As soon as I cube it, or raise it to the third power, that will make that number of units of distance cubed, whether it's miles or centimeters or feet, whatever it might be. And so on the right-hand side here, I'll end up with cubic units that will represent a three-dimensional measurement. So breaking down this formula into its pieces right now, again, much like surface area, there are technically only two variables here. Capital V, volume, whether that's what I'm solving for based on a given radius or whatever it is that I'm given to find the space inside of a ball, or the second one being radius, if I'm given radius solving for volume, or if I'm given a volume and then solving for the radius. Those are the two only variables in this equation, much like for surface area. It's just now I'm dealing with a cubed. And so the complicated part here that a lot of students get intimidated by, there are actually two pieces. The first thing they may recognize here is the fact that I'm dealing with a third power. Okay, from a simplistic view, whatever I'm raising to the third power, if you want to just do this on your calculator rather than trying to do something cubed, you could just do that something, that base, that radius length, whatever it is, times itself 3 times. That'd be something cubed. I'll show you the buttons on the calculator that you can do that third exponent in a minute, but we've actually done that before in previous unit as well. The other piece that people tend to be distracted by real quickly is the fact that I have this 4/3 fraction out in front. This is actually not much different than what we did with volume of a pyramid and or a cone, where it was 1/3 out in front. For the record, I'll go ahead and attach a YouTube video in our resources that shows like where this formula comes from. There's actually some calculus types of proofs too as to why this is connected to surface area. I'm not going to go into that because this isn't a calculus class. But this 4/3 out in front tends to intimidate students because they're like, God, I need to convert that to a decimal. Students just tend to be intimidated by fractions. But I'll make the same kind of suggestion here that I made with volume of a prism, or volume of a pyramid or a cone. Do this junk first. Pi times radius cubed, you'll get some value on your calculator. And then when I'm multiplying by 4/3, I would simply multiply by 4 and then divide by 3. I'll say that again. So when I'm doing this stuff right here, do this stuff first. Do whatever your radius is, cube it. You're going to see this in this first example. Multiply that by 3.14 if you have to round. And then when I multiply by 4/3, that's just the same thing as multiplying by 4 and then dividing by 3. It's tempting for a lot of students to first convert that to a decimal. That immediately approximates it. So just resist that temptation and multiply it by 4, divide by 3 as you would. The inverse operation here, just to describe this really quickly, if, say, I was given volume and had to solve for radius, the way I would move this 4/3 to the other side of the equation would be by division. So I divide both sides by 4/3. And here's where I'll remind you, anytime you divide by a fraction, that's just the same as multiplying by the reciprocal of that fraction. So if I wanted to move the 4/3 to the other side, say if I had to solve for radius, I'd be multiplying both sides by 3/4. Okay, so if I had to again solve for radius here, I'd multiply the volume by 3/4 to start with, and then it would be dividing by pi and then taking the cube root in that case. Okay, I don't think you'll run across a problem like that in your assignment, but if you do, I can answer those questions later. Okay, but essentially, for our intents and purposes, this is just the formula that we're going to be using for volume. So just be careful, particularly for the section, whether or not it's asking for surface area, in which case I'd use that first formula from the first clip, 4 pi r squared, or volume, in this case where I'd be using 4/3 pi r cubed. Again, the giveaway there is that area is in square units, so you'd have a squared part to your to your function. In this case, volume is a cubic or three-dimensional measurement, so you'd have a third power or cubed in the formula. All right, but let's go into these examples. First off, this first example is going to be super straightforward. Find the volume of a soccer ball. This is a real-life measurement. A soccer ball has a radius of 4.5 inches. And so we're going to find the amount of air that is on the inside of a soccer ball. The simple part here is that this 4.5 inch radius is literally just what I'm plugging in for lowercase r here. I'll do the calculator work much like the first example from the first clip and work my way through that. That'll find volume. Done. The second example will be a little trickier, and I'll talk about that in a minute, but let's go ahead and do that first example. You'll notice that they did not give us a diagram for this. Instead, they told us here is the radius of your sphere, your soccer ball, 4.5 inches, and they say, all right, identify the volume. So in this case, the fact that they're asking me about the volume of the sphere, I'm immediately going to use the formula that we have here, the second punchline to this section, 4/3 pi times r cubed. And since I already know what r is explicitly, I'm literally just plugging it in for r right here. So volume will equal 4/3 times pi times that 4.5 to the third power. And so this is where students, again, get a little intimidated because they see an exponent, particularly an exponent that's not squared, and they see this fraction out in front. But as I advised before, I'm going to deal with this chunk first, and as order of operations dictates, I have to deal with the exponent at the very beginning of this problem. So the very first thing I have to do here is 4.5 to the third power. So if that intimidates you, just bear in mind, something cubed is just something times itself 3 times. So 4.5 cubed is just 4.5 times 4.5 times 4.5. I get 91.125. Let's keep that number in the back of our heads because I'll show you how to do the cubed function on a calculator. Okay, so 91.125, that will be the result here. Here's where I'm going to zoom in on the calculator to remind you of this button that we talked about in the previous unit. This one right here. X to the y power. Big Ideas calculator has it. All of your calculators will have it as long as it's a scientific calculator. This will allow us to customize an exponent. So for instance, if I wanted to raise 4.5 to the third power, I'd start with 4.5. And then if I want to raise it to the third power, I'd hit that button. It's now waiting for whatever that exponent is. The exponent here happens to be 3. There's that 91.125. Okay, whichever way you do it, whichever way you're most comfortable with, feel free to use it. In either case, 4.5 cubed is this 91.125 result. And now I just have to finish doing the multiplication here. Volume is 4/3 times pi times that result. So again, in order to do this on a calculator, I would now multiply by the 3.14 or pi. So there's that 91.25 times 3.14. I get a gross decimal. Okay. And now to deal with the fraction. In this case, I'm going to multiply that result by 4, divide by 3. Multiply by 4, divide by 3. There's the volume of this soccer ball. 381.51. The units here are in inches, so these are cubic inches for three-dimensional volume. There is the volume of a soccer ball. Again, bear in mind, they did not have to give me the radius. They could have given me diameter or circumference. In either case, I'd first have to solve for radius r and then plug it in as we saw here. Just be careful again that I'd have to deal with the exponent first. Once I multiply these things together, the result after that cube times 3.14, I can multiply by 4, then divide by 3. All right, one more example to go. This one is a little trickier. Let me show the question first here. We are told that the surface area of a sphere, a ball, is 324 pi square centimeters. The square centimeters make sense because, again, that's area. So this is basically describing the amount of material needed to make this ball. 324 pi to make the exterior of the ball. Based on that value, our job here is to find the volume of the sphere, the space inside. But you will probably also recognize that surface area and volume, neither of those have each other in the formula itself. So this is actually going to require 2 steps. And the first step is going to involve that first piece of information they told us. We were told the surface area. So this is going to recall us back to the first clip, but when I'm told a surface area of a sphere, immediately the following has to be true. Surface area is 4 pi r squared. Okay, that is still true. That's the surface area of a sphere. The fact that they've told me what that surface area is, 324 pi, that value is simply going in for this capital S being the surface area. So I'm just substituting here, but surface area is 324 pi. That's going to still equal 4 pi r squared. Why is that valuable? Because in this formula, I can now solve for radius. Why would that be important? Because to solve for the volume of a sphere, as we have learned previously, I only need that radius r value. And once I have it, then it's just like this first problem where I'm plugging that value in and doing the calculator work. So let's get to it. So surface area is 4 pi r squared. I know the surface area of the sphere is 324 pi. Resist the temptation to make that 3.14 because we're going to find that the pi's cancel here in a second. But now I'm going to do my inverse operations. Start by dividing by 4 pi. This is something that we did in the first clip. You'll find that this eliminates right here. They cancel each other out. Pi's will cancel here on the left. So it's just 324 divided by 4. That gives me 81. And that's going to equal r squared. In order to undo the squared, I'm going to take the square root of both sides. I will have officially gotten r by itself once I get rid of that squared exponent. So r is going to equal whatever's here on the left. This one will happen to be a nice friendly number. The square root of 81 is 9. So I have solved for the radius of the sphere that has the given surface area. That's similar to a problem that we did before. In that other problem, we had to solve for the diameter, so we simply had to double this value. But now we're being asked about the volume of this sphere. So based on the surface area that we were given, we were able to track that down to solve this radius. Pretty valuable. But now I'm going to apply that radius to solving for volume, because the following has to be true for volume. 4/3 times pi times r cubed will give me the volume of this same sphere. And if I'm solving for capital V volume, the only other thing I need is this r. So I'm just going to substitute that r in. So volume is going to be 4/3 times pi times that 9 we just solved for, that radius, to the third power. And again, on your calculator, you could do 9 times 9 times 9. That would probably be a pretty fast thing to do. Or you could use that x to the y power button to do it to the third power. I'll go ahead and do that version. So I have 9. I'm going to use my x to the y button to customize my exponent, which is 3. 729. Had you done 9 times 9 times 9, you would have gotten the same result. So either way you're more comfortable with, whatever you want. So this becomes 729, whichever way you do it. Volume is going to be 4/3 times pi times that 729. So if I'm rounding to the nearest hundredth or 2 decimal places, I'm now going to do 729 times 3.14 for pi. I get that 2,289.06. That's again just this portion of the equation. So now when I multiply by 4/3, I'm taking this result, multiplying it by 4, and then dividing by 3. Multiply by 4, divide by 3, which is the equivalent of multiplying by 4/3. My volume here, rounded to the nearest 2 decimal places, is 3,052.08. The units here in this problem are in centimeters, so volume is in cubic centimeters. So this one was a little bit more tricky in that the information they gave me was a little more tedious to find that radius value, but still broke down to solving for volume, only required the radius. It just took a little bit longer maybe to get there, a little more complicated inverse operations, but once I plugged it in, it's just calculator work. But that will conclude Math 2 notes.